I will later, but I don't need it for this. I just moved it there because I was doing my work there. So no, I don't need it now. I'll do not. Thank you. Hey, John, how you doing? Hey, Shonda and John, how y'all doing? I don't think Shonda's actually able to listen yet. I think I spoke earlier before
I am
John.
doing well.
Good. I think I might have
Um,
spoke to you earlier when you weren't quite on yet.
yeah, I was dealing with my kids
Gotcha.
at the time. Um, I for, there was one question on the chapter 19 homework
Okay.
that I didn't understand why I kept getting the wrong answer. I hate to say I even cheated and did a check uh, or follow up with it,
Uh-huh.
and I followed letter by letter, multiplication by multiplication through the check, even used Excel, and I
Right.
still got the wrong answer. And I'm trying to pull it up so I can figure out what it is, but
Do you
I don't
know,
know if I
was it
have time to.
19 part one or part two?
Part one.
Okay, I was just looking for it and I'm actually in the part two by mistake. So let's switch back to part one and then we'll figure out which one you did or which one you had problems with.
Trying to pull it up.
Adding ice to water, drinking soda, specific heat of transformation, understanding heat conduction, thermal conductivity ranking task.
I know it's. I do know it was towards the end. I don't know. Don't remember exactly which one it was. It was late. I think Monday or Tuesday night that I did it.
Was it one related to planet Earth?
Yes, that was
Okay.
the one.
Yeah, so in your book, the paragraph explicitly tells you that you can assume the solar constant at the surface of the Earth is 1,000 watts per square meter. But they actually, in doing that calculation, they actually use 1,350. So I think that's why you're getting the error. I assume you got part A right, but part B was where you had problems.
Exactly, that was the one.
Yeah, so really the difference is there. All you have to do is take that 1350 and then multiply it by 8 hours, and then multiply that by the conversion from hours to seconds, and that'll give you the amount of energy that it's done. And then if you divide that by your answer to part A, you'll get like 10 to the 14th, whatever the actual answer is.
Okay.
So that's what was missing.
All
because
right.
they wanted part B, if I remember correctly, in terms of part A.
Yeah, that's exactly what they wanted.
Yeah, so all you have to do is, like I said, take that 1350, multiply it by 8 hours converted to seconds,
Okay.
uh, and then divide it by the answer you got in A, and that should give you the 10 to the 14th or whatever the ultimate
Okay.
answer will be.
All right. I'll give it a try again later tonight.
No problem. Feel free to
Thanks.
send me a photo by text if you have any problems with it, and I'll do what I can.
All right. No problem. Thanks.
You're welcome. All right. It's now 5:20. People are coming in. That's a good thing. We still only have 6 people here, but I think we need to go ahead and start on. John just asked me a question about one of the homework problems from chapter 19. It was the one about planet Earth. I happen to have just worked out that one for with some students of mine yesterday, I think, in fact. All you really have to do for that one, and by the way, I think it's number 10 in part one of the homeworks. And basically, all you had to do to get the answer that was like on the, I was saying 10 to the 14th, the answer is actually on the order of like 10 to the fourth or something like that. But basically, all you have to do is take the 1,350 watts per square meter that your book says is the solar constant at the outside edge of the atmosphere. I know it shouldn't be done this way. You should be using the one at the surface of the Earth, which is your book said was 1,000 watts per square meter. But you're going to use the 1,350 watts per square meter, and you're going to multiply that by 8 hours, and then you're going to multiply that by 3,600 to convert that 8 hours to seconds, so it'll cancel out and just make joules per square meter. Uh, and then, if I remember correctly, I think then you had to multiply it by pi r squared for the surface area uh, that contributes to it for the Earth, where r is the radius of the Earth. Once you have that number, you divide it by the answer you got for part A, and that should get it for you. Okay, I forgot the area part there, John. So hopefully you heard me that time. Anyways, anybody else have any questions before we get cracking? All right. All right, another student came in. Yay. All right, so here's the deal. We're starting in chapter 21 now. We will not obviously finish chapter 21 this week, so obviously the homework's not due this coming Sunday. I made the homework due a week from Sunday. But we are covering chapter 18. Excuse me, chapter 21. I suspect we'll be done with chapter 21 uh, Tuesday afternoon in this class. So in other words, I need one more class after today to do that. And then chapter 22 is essentially a 1 day chapter. So there's a high probability that you'll have chapters 21 and 22 due a week from Sunday. So just be prepared for that. I did have one of your fellow students email me or text me, I can't remember which one, about opening the face-to-face practice test. I did that for the other class because I had actually, for some reason, got my dates mixed up, and I ended up making that practice test disappear like January 31, and they didn't take it until like January, or excuse me, February 8th. So that was really bad on my behalf. So I did open it back up to them until this Sunday for anybody that wanted to give that extra credit. And then I also felt compelled to give them a couple extra credit points on that test because they didn't have the full bevy of things to practice right up until the test time. Still, I didn't screw up like that with yours, but I decided to go ahead and grant the student's request. So what I want to advise you that I did is I opened that practice test for the face-to-face test. I opened it back up, and for you guys, since you only meet on Tuesdays, you have until Monday night at 11:59 to do any attempts on that. I noticed in the grade book only 2 students attempted it. That's insane. I am literally making you practice tests out of the questions that I use for the test. So in principle, if you did it enough times, you would have seen every physics problem that would be on your test. At least that's the way it's been playing out for years. I don't think I've added a new question in close to 10 years, even though I reserve the right to do 80% of the points on any test to come from something other than the banks that those practice tests are made of. But like I said, I just haven't done that. So there's really, it's insane to think that someone's not taking these practice tests. That's the single most important thing you can do for learning the material, is to take it over and over and over again, because you get a different set of problems every time. And the more problems you work, the better off you'll be. So that was just a classroom note I want to make sure everybody got. Of course, I've also am recording this, and it'll be on my YouTube channel by tonight or first thing tomorrow morning at the latest. So if you missed any of those answers that I had earlier about the problem 10 and exercise, or in chapter 19, part 1, if you had any problems on that part B of number 10, I did mention to the students here exactly how I did it and got the right answer. So hopefully that'll help you guys. What I want to do now is I'm going to introduce you to uh, basically chapter 21, which is
Hey,
called electric
Professor,
charge. Yes.
I just have a quick question. You're
Yes.
talking about face-to-face test for practice test for test one, not another upcoming test?
Right. Not another, but the other one's coming up pretty soon. I think I might have already opened it. So
I didn't see it yet. That's what I was wondering about.
yeah, that one's going to come open soon if it's not already. I'm
Okay,
doing so many classes, I'd never know at a particular time exactly which ones I've opened. I'll look at it real quick
okay,
just to double check. But
okay.
yeah,
I'll
so
keep an eye.
be prepared for that other practice test to come up as well. Yes, I did already open up that practice test. It's called practice test 3, but that's for an online test.
I still didn't see it on there. Maybe it hasn't updated yet. I'll look again.
It's in the module that says practice test, and it's right below PT underscore F2FT01, and it's called PT underscore 03 dot dot dot. So
I literally just got notification on my phone about 5 minutes ago that it was now open.
that's crazy.
Okay, I'll just try to refresh and see if
Oh,
it half works.
oh, gotcha. If you got that verification, that's definitely for the practice test, because I just opened that 2 minutes ago. So that's probably why you got that message now.
Yeah, I don't. Okay, thank
You
you.
have,
You're
do you have
welcome.
a date for the actual next face-to-face test?
The next face-to-face test should be right verbatim from the actual syllabus. So if you look on your
Okay,
syllabus, those
cool.
face-to-face tests are sort of set in stone.
All right.
Okay, but the online test, which is what that other practice test I put up for, I've slated that for us to do it on February 19th. So I think that's a week from Sunday. So you literally could have in principle 2 sets of homework and a practice test all due a week from Sunday. So I would not wait on that if I was you guys. All right. So as I was saying, we're going into chapter 21. I have gotten all my weeks up to date to some extent. I'm checking now to see what I did with week 4 and week 5. So week 5 is this week, and yes, I did. I have in there. I'm going to go ahead and share my screen so I can show you guys this. So let me share screen. This time I'm doing it just the screen from my Canvas page. So this Veritasium Electricity Explained is just a wonderful video. Veritasium's a great group. They're doing great things with physics. I like the guy that does it. He's really good. I think he's from Australia. Might be New Zealand, but I'm pretty confident it's Australia. Anyways, he's really good. He works with the physics girl who, or I used to work with her, who's also very good. But this one doesn't necessarily have anything to do with this particular chapter. It has something to do with electricity in general, so that one's pretty good. But really, the most important ones are these MIT charge demonstrations and the demo videos. The Van de Graaff at Boston and the About Tesla's just fun stuff that I like to mention. I would normally spend a little time going through these, but we just don't have the time. I need to spend more time with you as students that are not face to face, but in internet classes. I really need to spend more time working on the topics as opposed to uh, the videos regarding concepts and stuff like that. So that's why I'm just leaving that up to you. And you need to get it from your reading as well, because there will be, of course, conceptual question homework set, and there'll be conceptual questions probably on the test. But the main thing I want you to understand is that what makes regarding those concepts, what makes a good conductor for electricity is the exact same thing, believe it or not, that makes it a good conductor for heat. So what we find out is the things that we consider conductors, which generally speaking, everybody knows metal is a conductor. Carbon's also a conductor, but it's not that great a one. Uh, but it's also not really, a metal, so to speak. But what makes the conductors good conductors is that they're not holding on very strongly to their outermost electron, in some cases more than one electron. And because of that, the electrons are free to move around the volume of the actual object. So if you have a chunk of wire that's made out of lead or made out of copper or aluminum or steel, basically the electrons are free to move around that wire. They're not tethered to a particular atom. And that means, unlike atoms, which are massive, or molecules, which are even more massive, uh, electrons are really, really light. And when they get bumped by a massive molecule with kinetic energy based on its temperature, that electron gets accelerated quite a bit. And then it goes on and shares that extra energy with, in principle, it can share with electrons, but electrons colliding with electrons is a fairly rare instance. Whereas electrons colliding with atoms and molecules is a real thing. And ultimately, that allows the average kinetic energy of the molecules in the structure, the wire, for instance, it allows them to increase on average rather quickly. That's why the loose electrons make a conductor, a good conductor of heat. The reason why it makes a good conductor of electricity is that charges moving is the very definition of conduction. So when you're talking about a current flowing through a wire, we pretend that that is a bunch of positive charges floating from the positive end of the power supply, which could be a battery or a power supply like we had in lab, or various other things. But basically, we pretend like positive charges leave the positive side of the power supply and then run to the negative side of the power supply. In reality, it's actually the negative charges going the other way, but there's really only one experiment you can do where that makes a difference, and it's called the Hall effect. And we're not going to do much with it. I'll show it to you when we get there. But the main thing is you can always pretend conventional current is right, which is pretending that positive charges are flowing around. So that's what makes them conductors. Now, additionally, you can do things like, for instance, you're all probably familiar with your walking around on a carpeted floor in the winter. Inevitably, you will go to grab a doorknob or something and it'll shock you. So what's going on there is you can imagine the rubber, say, in your shoes are actually very strongly attracted to electrons. So the atoms or molecules in the rubber of your shoes will readily steal electrons out of the carpet. And or if it's the other way around, and there's a hierarchy of things that's been developed by scientists over centuries, where we know that element A has more affinity for electrons than element B. And when we put them in an order so that we know when element A is up against a weaker element, C, D, E, or F, or whatever, then element A steals the electron, whereas element C, D, E, or F is losing the electron. So right now I'm pretending that that I know for a fact the rubber in my shoe is the stronger one. I'm not claiming that's a fact. I'm just saying that's a way we can think about it. So the rubber in my shoes might steal the electrons from the individual atoms in the carpet, and then therefore I become more negatively charged. Now, as I walk to the doorknob, I've actually become charged. The charge was transferred to me. So now I'm a charged creature. And if it's not too humid, because humidity, water molecules are polar, they're dipoles, which we're going to talk about in this chapter as well, but they act like dipoles. And because of the water molecules acting like dipoles, they have a positive looking in and a negative looking in. The negative looking in is the side with the Mickey Mouse head, because the Mickey Mouse head is the oxygen, and it makes a complete outer 8 when it takes 2 of the electrons from the 2 hydrogens. It basically behaves like neon, an ideal gas. The hydrogen end, which are the two Mickey Mouse ears, right between them is sort of a positive charge because they're deficient two electrons. So that's what makes the water molecule polar. And because the air might be sort of humid, that means there's a bunch of random polarized molecules of water all in the air, and they will quickly suck up the excess negative charge on my body. But if it's not too humid, then I can carry that for a little period of time. And as I walk over to a doorknob, the doorknob, which is made of metal, goes through a little process like this. So you can imagine, let's say this is the doorknob right here. It looks shiny, so I'm going to pretend it's metal. But as my finger comes near it, my finger, because it's got a buttload of negative charges on it, all the charges have oriented and positioned themselves all over the outside of my body in such a way that they are a maximal distance from each other. And that means this finger, for instance, has a negative charge on it. And when I bring it near this conductive metal doorknob, the positive charges in here, which are the nucleuses of the atoms that make up the molecules, and then the negative charges, the electrons, of course, they're free to move. So what's going to happen is they're going to be basically compelled to leave, the electrons will, because my finger is negatively charged and like charges repel. So it'll make a little circular area that's depleted of negative charges, and therefore it's now polarized. So we've polarized the doorknob by giving it a one side or one spot that's negatively charged, or excuse me, in this case, positively charged, and then the other end's like negatively charged, even though the total charge is still zero of the doorknob. Okay, so that's the difference between transferring charge, like happened to me by scuffing my feet, versus polarizing something by causing a polarized charge on a conductor. Now, if I bring my finger even closer and closer, it becomes more and more polarized, running off more and more negative charges and becoming more and more positive looking. There is a voltage, which is potential energy per Coulomb, that is being established between my fingertip and the nearest spot on the doorknob, right? So as I get closer and closer to that, that voltage actually, that potential energy actually increases. And eventually it gets to a high enough electric field strength that the air spontaneously becomes a conductor. Okay, it's still a crappy conductor, but if the voltage is high enough, you will ionize the molecules in the air, and then those ionized molecules will create a path from my finger, say, to the doorknob, or from the doorknob to my finger, and lightning will strike. The electric field strength that has to happen for air to become ionized like that is basically about 3 million 3 million volts per meter. That's another unit for the electric field that we'll learn later, but 3 million volts per meter. So that means if you really wanted to make lightning strike over a whole meter, which is like 39.37 inches, then you need 3 million volt difference between the one thing that's going to accept the lightning and the one thing that's going to send off the lightning. But because it's 3 million volts per meter, if you reduce that to volts per micron, then you would see basically you're going to have to divide that by a million, because a micron is a millionth of a meter. And what you'll see is, in fact, it takes 3 volts per meter, or excuse me, 3 volts, 3 volts per micron to ionize air. Therefore, if you get 1 micron away from the doorknob, you only need a voltage difference between your finger and the doorknob of 3 volts. Okay, so that's what happens when the actual doorknob shocks you, is basically lightning struck. Lightning struck either from your finger to the doorknob or from the doorknob to your finger. So that's the sort of some of the conceptual stuff that's got to sink in your brain. I think from your everyday experiences with with life, and with earth science and physical science that you had in high school and middle school and all that stuff, you probably have enough to go on the reading and that description I just gave you to help you better understand these demos. I might even find some time to discuss some of the demos during a lab meeting as well, but I'm not really sure yet. But definitely check them out. Feel free to ask me any questions about them. Or if you just don't understand it, feel free to set up a meeting with me. I stayed an extra hour last night after class because a person came to get help, and like I said, I'm here for that. So every day at 6:35 p.m., if you're logged in Monday through Thursday, you can ask questions about any of my classes. All right, so that's an intro to some of the phenomena that we encounter with regards to electricity and magnetism. Just like my shoe rubbing on carpet, you can actually rub fur on a plexiglass rod, and scientists have worked out which one of those is has the largest electron affinity, and the one that is, let's say it's the Teflon rod. The Teflon rod, if it has the highest electron affinity, it will actually steal the electrons from the fur, and then it'll become negatively charged. And conservation of charge, which is definitely a thing, dictates that the fur would then become positively charged by an equal amount. Okay. You've probably also done something like where you take a rubber balloon and when it's blown up, and you rub it on your head. I'm a little less capable because someone stole my hair, but in general, if you had hair, it would be a much better scenario. Otherwise, you just got a pasty white sweaty head of skin that's just going to rub against the stuff and not be much compelled to steal electrons because my head's so pasty white and moist. Normally because I'm a fat sweater. But anyways, you can, hopefully you did this when you were a kid, take a balloon, okay, rub it on your hair for, several seconds, rub it really good, makes your hair all messy and stuff like that if you care about such things. And then you can take your balloon, which is not a conductor, so those charges are not free to move. They're pretty much going to stay right there where they were rubbing on your head. Now you can bring it up against something that's not a conductor as well, like a piece of drywall that you have on your wall, or a piece of drywall that you have on your ceiling, and you can bring that balloon to the wall. And if the balloon, let's say, lost a bunch of electrons from that spot to your hair, now the balloon has a positive spot on it that's charged positive. That's going to compel the individual electrons in the wall or in the drywall or in the ceiling. That's going to compel them to at least get on the opposite side of the molecule they're attached to, because it's not a conductor, it's an insulator more so. And in doing so, that will basically show that particular side of the drywall slash wall slash ceiling will have the opposite charge of the balloon spot. So the balloon will look positive, and the wall slash drywall slash ceiling will look negative. And in fact, if you bring them together, because it's so hard to get the electrons to move in these insulators, it will completely stick to the wall or the drywall or the ceiling. So hopefully y'all have all seen that before, but that really does happen. You can do that, especially in the winter when it's not that humid. So give that a try. That's another nice little demonstration. And I'm going to go ahead now and begin talking about that chapter. But do check out these videos. Everybody sees them. Veritasium. Again, that's just one explaining that our idea of current going through wires is not exactly correct. It's like charges are going through wires, but that's not necessarily really what's happening by and large. Okay, so do check these out. Then there's also various links to my YouTube channel where I'm solving some physics problems. I highly recommend you seek out as many of those as possible, in addition to the ones in the book. Obviously, the ones in the book are critical as well. Let's go ahead and stop sharing this. I'm going to start sharing my iPad. Okay, so I'm sharing my iPad. It should come visible to you guys in a few moments. I don't like saying moments like there's a plural of that. Moments seem like an instant to me. And I should say a few seconds, maybe. Okay. What I want to draw your attention to first off when dealing with this is Newton's law of gravity. So Newton's law of gravity. I'm going to write the equation form and discuss a little bit the word form that basically he gave. And basically it says F, and I'm going to put a subscript G on it for gravity. You don't really have to do that, but I'm going to do that because I'm getting ready to offer you an extra credit using that symbol. So what Newton said is that there is a universal law of gravitation. And when I say it's universal, one reason it's universal is because the force applies to any two objects that have mass. So if any two objects have mass, then according to Newton, there is an attractive force between them, and it's always attractive, unlike Coulomb's law, which we're getting ready to learn about. That's attractive or repulsive. But in gravity, so far, we've only found attractive forces, and they're going to exist between any two objects that have mass. That's one reason it's called universal. The other reason you'll see in a second. So what he said was that force was directly proportional to the product of the two masses, so M1, M2, and inversely proportional to the square of the distance between them. So that's r squared. And the constant of proportionality is called the gravitational constant of the universe, which is that G right there. And I'm going to tell you that G is equal to 0.0000000000667 newtons meters squared per I said per coulomb, per kilogram squared. Okay, that's also 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Now, the other part of Newton's law of gravity it said was that the force that the attractive force that's created by this gravitational anomaly is in fact acting along the line that connects the center of mass of M1 to the center of mass of M2. So you have to sort of consider in space creating like a coordinate system and writing a spot where M1 is and a spot where M2 is. If M1 and M2 are particles, then it just acts along the line connecting the two particles, and it's always attractive. So if you're talking about the left particle and you want to know the force on it due to the right particle, then you put an arrow that ends on the left particle and that starts closer to the right particle and is lying along that line that connects the two. That's the way the force behaves. Okay, so if it's not two particles, though, then you have to do something called finding the center of mass for M1 and call that a point, and then find the center of mass for M2 and call that a point, and then draw a line between those 2 points. In practice, you never have to do that, okay? But I'm just telling you that's what you have to do. As luck would have it, Newton showed us as well that if something is spherically symmetric, then it will behave just like all of its masses right at the center. And that's true too with regards to charge when we were talking about the law of Coulomb that I'm getting ready to introduce you to. So you see that. Hopefully you all remember this Newton's law of gravity. You can also see now that there's no value of R that I can put in there that makes the gravitational force 0. That's the other reason that we call it Newton's universal law of gravitation, because it literally reaches across the universe. There's no R value you can put in there that gives it an answer of exactly 0. So in some sense, the force of attraction between, let's say, this tooth, right, and a star 700 light years away is not 0. It's dang close, and it's not going to feel anything, especially given how weak gravity is. But still, it's never going to be exactly 0. All right. Now I'm going to look at Coulomb's law. And Coulomb's law, which is not necessarily the proper name. I did some research on the history of this. It turns out that Cavendish and Ben Franklin and Coulomb all have a pretty good claim on this law being named after them. They all did the same work more or less at the same time. Obviously, Ben Franklin was obviously in the wrong place. Uh, he was spending most of his time in France in the 1800s, or at least the early, late 1700s, early 1800s. But before that, when he was most active scientifically, he was actually in America, which was a backwater and quite distant from anything. But here's the reason that I showed you gravity first. Coulomb's law, which I'll put a subscript C on. Again, I'm not going to usually use the subscript G and the subscript C. I'm just putting them for the extra credit problem I'm going to give you in a second. But the law of Coulomb basically says that the force between two particles that are charged, so there's the key thing, the two particles have to be charged. And hopefully you all know that like charges repel. So that means two negatives will repel each other and two positives will repel each other. And unlike charges attract, that force is directly proportional to the product of the charges. So I'll say Q1, Q2, and it happens to be inversely proportional to the square of the distance between them. Okay, so notice it looks just like gravity. Here's a big difference. And by the way, this is one of the rare times I actually use that K. Okay, that K doesn't even have a name that I care to mention or anything like that. It probably has a name, but no one uses it. No one that's serious about electricity and magnetism at all uses K. What they normally use is this version, which would be Q1, Q2, and it isn't necessarily easier to write, but I'm giving it to you anyways because this is the important one. 4 pi epsilon naught r squared. Now, I'll also tell you that just like Newton, Coulomb would have said, and the force, whether it be attraction or repulsion, that force will act along a line connecting the center of charge of Q1 to the center of charge of Q2. Again, if Q1 and Q2 are particles like electrons and protons, then you just draw a line from one proton to, or from one particle to the other, and along that line is where the force will act. Then it's just a matter of deciding, does it point to the left or to the right, based on it being attractive or repulsive. So here's the big part. K, which is actually the same thing as 1 over 4 pi epsilon naught, is equal to 8 point, and I'm going to say approximately, 8.99. Actually, let's not use scientific notation. I'm going to do like I did before. I'm going to say approximately equal to 899. And now I'm going to say 0, 0, 0, 0, 0, 0, 0. Notice those digits are not truly zero. We know a lot of them, and they're not zero. I'm just putting it there to show that there's really placeholders. And then, of course, the units for this one happens to be newtons meters squared per coulomb squared instead of kilograms squared. And we can also write this as 8.99 times 10 to the 9th newtons meters squared per coulomb squared. But the reason I took this time to write it this way, and the reason I showed you Newton's law of gravity with Coulomb's law, is you see that they're both the same formulas, right? It's a product of some characteristic. In the case of gravity, it's mass 1 and mass 2. In the case of electric force, it's charge 1 and charge 2, which are measured in coulombs. And it's inversely proportional to the square of the distance between the two objects, which in the case of gravity is m1 and m2, and in the case of Coulomb's law is q1 and q2. But when you look at that, you then realize, well, wow, gravity's got this multiplier that's like 0.10 zeros and then 667. So gravity's really, 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 really weak. And then you look, Coulomb's law has got this multiplier that's like 9 billion. So that's really, really, really big. So you can already start to see that the actual electric force that Coulomb's law describes should be way, 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 way stronger than the gravitational force. Okay. So for extra credit, this is a problem I'm going to give you. Calculate FC and FG for the proton and electron in an unexcited hydrogen atom. Oops, I left off the N. I was wondering why my A was looking like an N. Then calculate. I don't like my L. It turned into a C looking thing. Then calculate F Coulomb divided by F gravity equals question mark. Okay. That means you're going to have to look up the mass of an electron. That means you're going to have to look up the mass of a proton. That means you're going to have to look up what we call the Bohr radius. And you're going to have to look up the charge of the electron. And you're going to have to look up the charge of the proton. Okay. And then you can do all that. I will tell you that the magnitude of the charge of the electron or the proton is it's actually listed as a symbol E, and its value is 1.602 times 10 to the negative 19th coulombs. A coulomb, by the way, is a really big unit.
Yes, Professor, I had a
Yes.
question about that. And it was just about the significant figures.
Uh-huh.
After I did the calculations, I used the constants, just as like, they're exact.
Right.
But then, I just put it down to like two significant figures because some of the measurements I looked up for the I think for the I'm busy right now. For some of the either the electron and the mass of the proton, they were only in two significant figures. So is
That'd
that
be
going to be
fine.
acceptable?
Yeah,
Okay, that's
that'd be
all.
fine. I would say a general rule that you should use is always use 3 sig figs. But yeah, if you just don't happen to find them and you use 2, that's fine, especially for this calculation.
Okay. Okay, thanks.
No problem. Good question. All right, so we've got that covered. Now I need to actually solve some problems for you. I think the main thing I'm shooting for here is, of course, some understanding of how this works. So what I need to do really is give you an example of how to use this Coulomb's formula to calculate an actual force. Okay, and then I'm going to introduce the concept of a vector field so that we can make a little bit more sense out of it. This was, immediately when Newton devised his theory of gravity, he stated, I don't know how this is possible, but basically I'm going to use it because it's really, really helpful. And, he could do certain things like he could make sense of the orbits of the planets around the sun and of the moon around the earth, and all those numbers worked out. And in fact, with Newton's gravity, you can get to the moon, you can get to Mars just using Newton's stuff. You don't have to use general relativity for that. Now, there will be some problems. You'll have some clocks being off by a little bit, but you can still do it. So, just to let you know that that's a possibility. So, we have to keep that in mind. So, what I want to do is show you how you take this formula, which gives you a magnitude, but along with the law where they stated the line along which the vector acts and stuff like that, you should be able to make a vector out of it. So what I'm going to do is I'm going to ask you guys what is the total force on particle 2. Okay, so let's draw our particles. I'm going to say there's a particle right here, and there's a particle right here, and there's a particle right here, and there's a particle right here. This one I'm calling 1, this one I'm calling 2, this one I'm calling 3, and this one I'm calling 4. This one's going to have a charge Q. This one's going to have a charge Q. This one's going to have a charge of 2Q. And this one's going to have a charge of 3Q. Okay. And I didn't draw it exactly correctly. Let me fix that. This was supposed to be a square, so I really have to put this down here. And that'll allow me to do this real quick. Boink, boink. And I don't mind where there's a mark, but that makes it work okay. So now what I'm going to do is I'm going to go ahead and introduce a coordinate system. And it doesn't have to be this one, but this is the one I'm using. So there's my x-axis. There's my y-axis like that. Okay. What we want to know is what is the total force on particle 2. Notice all these charges are positive. R, the Q itself is a negative number, and that'll pan out when we go to plug in what Q is. But I'm going to treat everything as if it's really just Q, Q, 2Q, and 3Q. Okay. And I want to calculate the force on particle 2, which is in that top right corner. Okay. So what we know about forces, we learned last semester that basically if you have more than one force acting on something, then you just have to add them vectorially. So I can tell you that F total, which I'll also call F2 as a vector, is the force on 2 due to 1 plus the force on 2 due to 3. Notice how I skipped 2 due to 2 because obviously the thing can't put a force on itself, plus the force on 2 due to 4. Okay, so that's how we're going to work this out. I need to first get the magnitudes of these forces. So I'm going to say F21 is equal to, let's call this, notice it's particle 1 has a charge Q and particle 2 has a charge Q. So I'm just going to write Q squared over 4 pi epsilon naught. And here's where I'm going to say this distance from here to here is just A. And this distance from here to here is also A. So I think you can see that the separation between Q and Q is A. So I'm going to write A squared down here. Okay. Now I look at this and I realize that both charges 1 and 2 have a charge of Q. So they have the same sign basically, and therefore they're going to be repulsive. Now I'm treating Q like it's positive, but like I said, if it turns out to be negative, when I put the negative in, it'll sort of take care of itself. The main thing is if Q is negative, both will be put negative, so they're still repulsive. So what I know is that the line between them is the line along which the force is going to act. So what I'm going to do is I'm going to use another color. Let's use red. And I'm going to say F21 is this way. Does that make sense to everyone? Everybody see that object 2 is the one we're trying to find the force on. And according to this red arrow I just drew, it's trying to move to the right because charge Q1 is pushing it that way. That's what repulsion means. Does everybody get that? I will let you guys know that I never put the signs in. Okay, and you shouldn't either. I've never had a reason to, and I've found that people that do tend to get wrong answers a lot. So don't do that. Okay, you work out in each case which direction, or first whether the force is repulsive or attractive, and then using that, figure out along with the line connecting the two particles, figure out which direction the vector is going to point. Okay, now that I know F21 is actually pointing to the right, and that happens to be on my positive x-axis, then I can say F21 whoa, F21 as a vector is going to be q squared over 4 pi epsilon naught a squared, and it's just going to point in the positive x direction, so I just put an I hat by it. Okay, I'm going to do F2, let's do F23 now. So F23 is again equal to, in this case, it's Q and 2Q. So I get 2Q squared over 4 pi epsilon naught. Notice their separation's also A, so I'm just going to put that as A squared in the bottom. So I now have the magnitude of that force as well. In fact, using my red line, you know that it has to be along the line connecting the two particles. And remember, in geometry, when you say line, that's sort of understood to be infinitely long. Okay, so it's okay for me to extend past 2 and 3. I could, in fact, continue it down here if I wanted, but I want to know the force on 2. So in this case, Q and 2Q again have the same sign. It appears they're both positive, therefore they're repulsive. Therefore, charge 3 is pushing up on charge 2. So I'm going to put this red vector right here, and I'm going to call that F23. Everybody follow that? So F23 is going to become 2Q squared J hat. Notice that's a J hat, not an I hat. Over 4 pi epsilon naught A squared. So now we have the vector part of that. Now I'm going to do F24. F24 is a little more complicated because the distance is not just straight A, so we have to work that out. But we see the charge is Q and the other charge is 3Q, so I'm going to get 3Q squared for the product of the charges. I'm going to get 4 pi epsilon naught for the bottom part. And then does anybody know off the top of their head exactly what the distance is between particle 2 and particle 4?
Square root 2a.
Exactly. Because each side is A, you'd get the hypotenuse would be the square root of a squared plus a squared, which is 2 times a squared, and that gives you the square root of 2 times a. When we square that, that's going to become, in fact, I'm going to make this into an 8 now. And now I'm going to say it's a squared, because what happened was this distance was the square root of 2 times a. When we squared that, we got a 2, and that made that 4 into an 8. Does that make sense to everyone? Okay, so there that is, and I can now make this into a vector. For instance, I know that 3Q and Q again have the same sign, so it's repulsive. So I also expect this one's going to be a little weaker because it's farther away. but it might be a little stronger because it's a bigger charge. So this one's going to be F24 on the diagonal here. And notice this angle, because it is a square, this angle is 45 degrees exactly. Okay. So what that tells us is F24 sub x would be the magnitude of F24 times the cosine of 45 degrees. And it points to the right. So I'm going to put a plus there. Similarly, F24 y points up, and therefore I'll put a plus there as well. So it's going to be F24 sine 45 degrees. Now, we know that sine of 45 and cosine of 45 actually happen to be the same thing. They're the square root of 2 over 2. So this gives me, let me change my colors here. This gives me F24 is equal to, here I'm going to notice that I have something common from all of these forces. Notice all of them have a q squared over 4 pi epsilon naught. So I'm going to make use of that right now and write q squared over 4 pi epsilon naught. And they all have an a squared, so I'm going to put that down there too. Okay. Now what I'm going to do is say that's the almost the magnitude for F24. In fact, the magnitude is actually that times 3/2, but also times the cosine of 45, which would be the square root of 2 over 2, like that. Okay. So does everybody see that that is what the x component should be? So I can put just I hat there. And then I'll put a plus for the j hat or the y term. Again, the magnitude is 3/2 times the stuff I got out in front. So I'm going to put 3/2, but then I got to multiply it by the sine of the square, sine of 45 degrees. So that's going to be the square root of 2 over 2 again. And that will be multiplied by j hat. And now I have all the vectors, and they're already in IJK notation. So that means the addition will be super, super, super easy. Any questions on this? Okay. So what I'm going to do now is I'm going to say F total is, so this is F2, which I said was F total. That's going to be, I still have that common q squared over 4 pi epsilon naught a squared. So I'm going to make use of that. Just because it makes life a lot easier to write all this stuff. So now I've got to add all the x components, which are the ones that have I hat in front of it. So you see this guy has I hat in front of it, and this guy has I hat in front of it. So I'm going to use those. And q squared over 4 pi epsilon naught, it comes from the F21. And notice that's exactly the whole thing that I have out in front. So I just put a 1 there. But now I've got to add that to 3 root 2 over 4. And then why am I writing all this in red? Oh, well, I'll leave it. I really don't want to do that. Sorry about that. I'm going to write it in black so it won't be so distracting. So that's going to be 1 plus 3 root 2 over 4, all that in the I hat direction. And now I've got to do the same thing for my y components. I'll use a different color arrow to remind us that. So this time I have a y component there, and I also have a y component there. So I'm going to do like I did before and put a plus and then a parenthesis. And what I see is F23 has a 2 in front of it, but everything else is the same. So I'm just going to put 2 plus, now this is going to be 3 root 2 over 4 again, just like the last one, and then times j hat. So that technically is an answer, but like I told you about vectors, you need to, at the drop of a hat, be ready to write it as a magnitude and direction format as well. So that's what I'm going to do now. Even though I've got the right answer already, I definitely want to follow up on that and do the vector stuff so y'all are really comfortable with your vectors. Anybody have any questions so far? All right. So I'm going to go ahead and do this now. So the first thing I'm going to do is realize both of my components, notice the both of the components are positive. You can tell that because F21 was positive and pointing to the X direction, and then F24 went diagonally up and to the right. So that meant its X component's also positive. And then F23 is all up, so that's in the Y direction is positive. And of course, F24 had a positive Y component because it's up and to the right, so it's positive as well. So that's why we have all positive components. So what I want to do is draw a coordinate system and put that vector in it. So this vector, F total, which I'll call F2, is now going to look like this. And it looks like, okay, it looks like the Y one's going to be a little bit bigger. So what I'm going to do is I'm going to take first and say, this is the X component, and then this is the slightly bigger Y component. Therefore, this right here is F2. Okay. And I'm going to call that angle phi. What I'm going to recognize is the magnitude of the Y component is that stuff that I chose to factor out. So I just put in parentheses with dots in it. But in addition to that, it's going to be 2 plus 3 roots of 2 over 4, which I could call 8 plus 3 roots of 2 over 4. That would be right. And then this one, the X component, again, is that same common factor. But in this case, I could write that as 4 plus 3 roots of 2. So I'll say times 4 plus 3 root 2. All of that, which I'll put in parentheses to make it clear, all of that divided by 4. Okay? So this answer, for instance, we can work it out a little bit. 3 root 2 over 4. That's 1.0607. So I'll write it over here. 3 root 2 over 4 is approximately 1.0607. Okay. And then from that, you can tell that this number is just going to be roughly 1 plus that. So that's going to be 2.0607. And then this one, of course, is going to be 2 plus that 1 point. So this will be 3.0607, like that. Okay. Now all I have to do is take F2 is equal to the square root of 2.0607 squared plus 3.0607 squared. And that's going to give me oops. And then That one's 2 plus that, so it'll be 3, 0, 6, 0, 6, 0, 7, 2. I'm going to square that sucker. So that gives me the square root of, oh, and I should say, let me do something real quick with this, lest y'all catch me. Okay. This also has that common factor in front of it. Okay. So I now have the square root of about 4.2463 plus 9.3676. Again, that's times those symbols that I factored out. So that gives me roughly the square root of 13.61. And therefore the magnitude is 3.6897 times q squared over 4 pi epsilon naught a squared. So that's what the magnitude is. I can also say that phi is equal to the inverse tangent of, I'm going to revert back to that, to those digits there. So I'm going to say 3.0607 over 2.0607. And I'm going to take the inverse tangent of that. 3.0607 divided by 2.0607, close parentheses. That gives me 56.05 degrees. So F2 I can also write as is also equal to 3.6897 q squared over 4 pi epsilon naught a squared. Uh-oh. That was really bad writing it that small, huh? Okay. So times 4 pi epsilon 0 a squared. And that's going to be at the angle. Notice that angle is measured counterclockwise from the positive x-axis, so it's in our standard position. So I'm going to say that's at 56.05 degrees. And that's another answer. Anybody have any questions on that?
No, I'm okay. Thanks. It's very interesting though.
Yeah. Yeah, so that's the way you are going to deal with these. Obviously, it'll normally be where you have numbers, but numbers sometimes makes it a little less transparent when you're looking back at your notes and trying to make sense of how, I got the answers that I got. Maybe the symbols will help you for that a little bit. Probably wouldn't hurt if I separated this down here a little bit more too. So let me clean that up just a tad. So now I'm going to go back and get my color that I was using.
I do have kind of a quick question about the electricity molecules and the charges and stuff,
Yes, ma'am.
or atoms, I mean, or whatever. It's just like, okay, and I kind of had a hard time understanding this. I was reading about it. So technically, they don't really flow. The energy is just being passed along from electron to electron. So the electrons kind of stay in one place and vibrate or something.
No, the
Is that how it
electrons do
works?
really move. In fact, when we get to the chapter on on current, we'll actually calculate not only that they move, but we'll see that they move, but they move very slowly, which is surprising. And
Okay,
that's
because
part of
yeah,
what that Veritasium video gets for you, is you see that something else is going on as well.
yeah, because there's a part where they really get agitated, the electrical negative energy, and they pass the charge through each other without moving. But you're saying they also slowly move through a, let's say,
Yeah,
a,
you'd
a
think since lights, come on instantly, when you flip a switch, it appears that the light
yeah.
turns on almost in an instant. You'd think that means they're traveling at the speed of light or something, but it turns out they're only usually moving a few centimeters per second.
Okay, yeah, because I've read various theories on that. Sometimes, like it's moving at the speed of light, as opposed to they're just stationary in place, moving very
Right.
quickly in like a vibratory motion or something. And then,
Gotcha.
that's all. It's like,
All
oh,
right.
it's very
Well,
interesting.
let me
Thanks.
now, so I mentioned the problem about action at a distance. So this formula, F equals, Q1, Q2 over 4 pi epsilon naught R squared, uh, really makes it seem like there's some magical force reaching out across space from Q1 to Q2 or from Q2 to Q1 and pulling on it, even though they're not touching each other. So what scientists tried to do, and Michael Faraday was one of the first people to start talking about this, even though he didn't have the mathematical background to make much sense of it. And vector calculus and vectors in general weren't even invented yet, so he couldn't do it for so much. But what they decided to do was, let's imagine for a second that the force, and I'm going to write this down here, that the Coulomb force, which is
Yeah.
equal to, I'm going to write it with different symbols this time. I'm going to write it with a Q and a Q instead of Q1 and Q2.
Uh,
Is 4 pi, and your speaker's still on there, Shonda.
oh, I'm sorry.
No problem.
I'm sorry.
So you see QQ over 4 pi epsilon naught. That's the actual magnitude of the force. What I want you to think about is, imagine instead, if we imagine charge Q causes I already wrote that. Sorry about that. The space around it to change a little. Or I'll just say change some. Then when little q comes into the space around q, it feels a force due to the weird space. So what we're imagining is that charged big Q there is actually altering the space around it in some way. What that way is going to be is a vector field. It's going to create a vector field. And then when you bring the charge little q into it, little q feels a force, but without that charge there, you don't know anything except for maybe that you might be able to build some kind of detector to detect the weirdness of the space, but you don't necessarily know the force is going to happen until you bring a charge in there near it. So if you do that, then you might be able to say, consider the idea that the space was altered to q over 4 pi epsilon naught r squared at a distance of R from the center of charge of Q. Okay, so in other words, because we know Q has some role to play, big Q, and little q has a role to play, let's take the little q out of it and think about what could be responsible for the weirdness of the space, and therefore only include Q and how far you are away from Q. This quantity, when you do that, this becomes the electric field. It's a vector field. And a vector field basically assigns to every point in space a vector. So it literally comes up with a vector for every point in space. A scalar field would just be a number. So like a scalar field might be the temperature mapping of a room. So if you took every X, Y, Z coordinate in a single room and you took the time to determine the temperature at each of those spots, then what you had is the list of all the points of a scalar field called the temperature field. This is a vector field though, so at each of those points you'd have to assign it a vector quantity, and in this case, the vector direction will be the direction from Q to R. So the vector field will point from Q to the point at which you wish to know the field E. Okay, so that's how we're going to define it. And from that, you have to realize that, hey, if I do this, then wouldn't the little q also cause a disturbance in the space? And to be consistent, you have to say, yeah, that's going to do it too. So in practice, what we have to at least think about, though I've never had to physically do it, okay, I have to think of a limiting process so that Q doesn't materially change that quote unquote weirdness of the space around it. So what we ultimately do is we define the electric field as E is equal to the limit as lowercase q approaches 0 of Q over 4 pi epsilon naught R squared. And I'm just going to say, let's put a D hat where this vector represents the field direction. Okay, that's liable to change from one point to the other, but the main thing is, since I wrote E with a vector symbol on the left-hand side, I had to write a vector on the left, on the left-hand side, so I had to write one on the right-hand side. So I just called that D. And notice with a hat over top of it, this means a unit vector, so I haven't screwed up the magnitude at all. Because if I multiplied it by any vector other than a unit vector, then the magnitude wouldn't be right. When we do that, we now have the neat little relationship that F is equal to Q times E. So these are the big important equations, if you will. I will circle this one in green just because I got to go over that red writing over there. And I'll circle this one in green because I did the same thing there. Okay, so there's our equations. But what I really need to do is I need to be able to write this equation in a form that gives me the vector. Okay, so what I'm going to do is I'll imagine a coordinate system. So let's imagine this is my x-axis, this is my y-axis, and this is my z-axis. Let's imagine over here is the charge Q, or specifically the center of charge of Q. Okay, so Q could be a point particle, and which is right there, or Q could be some blob of particles, but that dot represents the center of charge for it. So I could do like that, right? And what I'm going to do with this is I am going to specify a vector that's called R sub Q. Notice it just comes from the origin and points to the charge causing the electric field. Now I'm going to put another point over here. And this I'm going to label P as the point at which we want the, whoa, I started thinking about the next thing I was writing. The E field. Okay, so here I'm going to draw another vector, and that's R sub P vector. Okay, now according to what I just told you, the electric field should point in the direction that a positive charge would want to go as a result of the charge Q. So I could draw, for instance, a little dotted line right along here, and Q could have a sign negative in it, but we treat it like a positive and everything will work out. So if I pretend Q is a positive and I put a positive charge over there at point P, which direction will the force, or excuse me, will the electric field point? Will it point towards the RP or towards the RQ? Remember, like charges repel and unlike charges attract. I'm wanting to put a positive charge at the end of vector RP. And also, can anybody think of a vector relationship or a vector action you can do using RQ and RP to get a vector that lies along that dashed line? Anybody tell me a mathematical operation you can do with RP and RQ to get a vector parallel to that dashed line? Anyone? Your speaker's off, Shonda. Sorry.
Yeah, I forgot how to do that. I just learned it like a month ago, but I've been doing probability and statistics.
Yeah, it's a subtraction. So
Yeah, you just subtract. Okay, that's right. Yeah.
there you go. So this vector, if I wanted to make a vector, I could make it right here, and it would actually not only point in the right direction, it would have the exact right length for the distance between Q and P. So this vector would be RP minus RQ. And not only that, usually what happens is you break the charge distribution, which could be that little blue blob right there. You break it up into little differential charge elements, call them DQ. And then you maybe would call this RP minus RDQ. So if I'm doing that, then what I'm going to do is say the electric field due to that little differential charge element is dE, and it's actually equal to dQ over 4 pi epsilon naught. Now I need the distance between Q and P. Well, that's the magnitude. Oh, man. That's the magnitude of RP minus RDQ. So I'm going to put that here. Notice I changed the subscript from Q to RDQ. Okay. Now, in general, you would say, well, that needs to be squared. But I also need to put the direction there. So I'm going to write, dang it. Ugh, it's making me mad. I know we're about out of time. So I'm going to put RP minus RDQ. And that went bad too. I'm going to put that vector right there. But by doing that, notice, like I said before, if I multiply a magnitude that's the correct magnitude by a vector that's not a unit vector, then I change the magnitude to the magnitude it had times the magnitude of that vector. So in order to make this correct, I've got to account for that extra RP minus RDQ distance I just multiplied by. So to fix that, I'm going to change this 2 to a 3. And that's very, very important. You got to notice that. Okay. So that's the formula we'll use. And I will tell you that in general, dq will either be equal to lambda times a dl. In other words, it's going to be a certain number of coulombs per meter times dl, which could be dy, dx, dz, dr, whatever. Or it could be sigma, which would be a number of coulombs per square meter times dA, or it could be rho, which would be a number of coulombs per cubic meter times dV. Okay, so that's generally what the formula we'll use. I will make use of this next time. One more thing I just want to point out to you. Electric dipole is this. Just so you can start doing your homework. You can get all this from the reading, but electric dipole is given by the symbol P, and it's Q times the D vector. So it's a vector quantity. And what it basically consists of is a negative charge and a positive charge. This charge is negative Q. This charge is positive Q. And if I drew a vector from the negative one to the positive one, then that vector would be my little d there. Okay. So that's what the electric dipole moment is, P, and it's given by taking the magnitude of either one of those charges and multiplying it by the distance between the two charges. And then, of course, making it a vector by making it point from the negative charge to the positive charge. And that's it. You guys are free to go. I ran over by 3 minutes. I apologize for that. Please, before you go, I know one person just slipped out. Before you go, type in your name to the chat so I can use it as a roll sheet, and you're free to go. If anybody knows who just left, will you please type their name in there too? I see Kaylee had to split. Gotcha.
Just a question about the Q and the Q. Q is for the field, and the large Q is for the field, and small Q is for individual electrons or
Yeah, it's like a
components like
test
that.
particle. Mhm.
Okay, yeah, just so that does matter though, for instance, to
You can
write,
use any symbol. Like I'm probably never going to use capital Q for almost anything.
right.
But yeah, you just needed something to separate the two, and 1 and 2 I didn't think was significant enough. So I thought I'd use a big Q for the source of the field and a little Q for the test charge of the field.
Okay, all right,
Yeah,
thanks.
you're welcome. You can see some videos where I actually use this formula already on my YouTube channel, so feel free to do that. It looks like everybody but Shonda's gone. Yeah, it does look like that. I'm going to go ahead and stop sharing. Anybody have any questions before I split? All right, it looks like that's it. All right, have a good one, everybody. Bye-bye.